Solomon codes are widely used codes. So, I mean, there you can come across many applications from data storage to transmissions. However, recently, there are two applications I want to point out without giving details. If you want to, if you are interested in doing research by using these codes, you may check in the coding theory site what is called locally recoverable codes. Or if you are interested in cryptography, you may also check private information retrieval. So this theory is interested in retrieving data from a database without revealing which data is requested. And roughly speaking, locally recoverable codes are interested in. So, I mean, we have a code word, so we have a corrupted bit or coordinates in our code word. So by the corruption, we mean it can be deleted. So this theory is interested in recovering this corrupted data by using the other coordinates and as small as possible. So you may come across the applications of the Reed-Solomon codes in these directions, and at least I can recommend the resource which is called Network Coding and Subspace Designs. And there's a special section which also explains the relations between locally recoverable codes and the private information retrievals. However, for the moment, we're interested in their structure in algebraic function fields. So let me redefine the Reed-Solomon codes in terms of the rational function fields. And by the notion so far, indeed, we can guess that if we work with a polynomial space of degree at most k minus 1, we know that in the rational function field, we can represent them in terms of the Riemann space of the spatial divisor k minus 1 times p infinity. Here p infinity denote the pole of the transcendental x. And obviously our constant field is going to be finite field. And for the Reed-Solomon codes, we consider particularly length as k minus 1. However, in this rational function field, we know that there exists q plus 1 rational places. So that means later we will see that it will be possible to extend a bit more, extend the length of the code to q or q plus 1. But again, for the Reed-Solomon setting, we consider the evaluations of polynomials at the powers of beta to the I. So that means we can interpret that these evaluations of functions at given places, here each place will be denoted by the linear polynomial x minus beta to the I. So that means Particularly, we will be interested in the evaluation. So that means we will consider the residue class maps of the functions or the point functions from this Riemann space. It's given pairwise distinct places, PIs. And since this is rational place, this residue class field for each I is going to be isomorphic, the full constant field FQ. So to represent all evaluations, let me fix some notations. So if we consider the Ritz-Solomon codes with respect to this notation, to represent all these given distinct places, we will introduce a divisor as the sum of these distinct rational places, and this D will appears as evaluation D in order to represent that we are evaluating functions at given places Pi. And the second thing I want to point out, here we consider the evaluations of the residue, evaluations in terms of residue class maps, but when we, if you recall the definitions of the residue class map, we will also consider the case when the evaluation is infinity. However, here support of D, so that means this given n distinct places is different from the place P infinity. When we evaluate a function at given Pi, infinity is not going to be the case, because for any non-zero function in the Riemann space of the divisor k minus 1 P infinity, we know that it can have only poles at P infinity and of order at most k minus 1. So that means F cannot have poles at given Pi's. Pi's, because all Pi's are distinct from P infinity, and F can have only poles at P infinity of order at most k minus 1. So that means all functions in this Riemann space are also discrete valuation rings OPIs. So that means when we evaluate them at Pi, infinity cannot be the case. And the third part I want to point out, in the rational function field fq of x, we know that any divisor g of degree k minus 1 is equivalent to the divisor k minus 1 p infinity, because the degree of the g minus k minus 1 p infinity is 0, and so its degree is bigger than or equal to 2g minus 2, and we can apply Riemann's theorem, and its dimension in this case is bigger than or equal to 1. And we know that in this case, this divisor is indeed principal. That means there exists an auxiliary function u such that g can be written, or k minus 1 p infinity minus g can be written as the principal divisor of u. So probably in the discussion, as I explained, one of the discussion session, this equivalence allows us to consider a bijection between the Riemann space of k minus 1 p infinity and L of g, and we can explicitly write the basis of the Riemann space L of g in terms of this function u and the basis of k minus p infinity. And indeed, we can extend the definition of the Ries-Solomon codes, so that means we can extend their domain, or we can generalize this domain. By a divisor of degree k minus 1. Or let me write it more clearly. In general, we can consider the Riemann space of a divisor G who has disjoint support with D. So any PIs, any given distinct rational places, does not lie in support. And thanks to be able to write the basis, its basis explicitly, when we consider the evaluation map, in this case, its image again is going to be linear code, and we can explicitly write its generator matrix by considering the evaluations of the functions at given places pi. And the last entry u of p1 x to the k minus 1 of pn. So here, another thing I want to point out, the length of the Ries-Solomon codes, as we mentioned before, is q minus 1, but we have q plus 1 rational places. So that means, can we extend the length from q minus 1 to q or q plus 1? And next, we will understand these cases under the framework of generalized Riz-Solomon codes.